Okay, so guys, welcome back. This is Discrete Optimization, Local Search, Part 5. And what we're going to see today is sports scheduling. Remember, when we did the first introductory lecture, I talked about scheduling and NFL scheduling. So today we're going to talk about some really hard scheduling problem, okay? And the key point, the reason why we want to do this is that we're going to talk about a really complex neighborhood, a beautiful neighborhood, which was done by, some of my students and colleagues, Aris, Yanis, and Laurent. And they really got obsessed with these problems. And I'll tell you some of the results at the end. So sports scheduling, I told you at the beginning, it's big business, radio and television network are willing to pay a lot of dollars. And because a lot of the sport leagues now, have very high revenue. And, let's say in the US, we talk about baseball, basketball, football, and hockey. In other countries, you'll talk about footy and soccer and other things. But in all cases, it's a big business, okay? And so what I'm going to talk about today is called the traveling tournament problem, TTP for short. And it's an abstraction of Major League Baseball in the United States, which was proposed by Kelly Easton, George Nemoser, and Michael Trick. And so you will see, it's kind of a beautiful problem. It's very simple to state. It's amazingly hard, okay? And it basically abstracts, Major League Baseball, which is more complicated, but it's essentially the essence of Major League Baseball. Now, why is it complicated? Because you'll see two things. You'll see very complex feasibility constraints, and I'm going to explain them to you later on. Okay, but essentially home-away patterns, the fact that teams cannot play too many times at home or away. And then it has a very complex and global objective function. You want to minimize the total distance, which is basically traveled by these teams. And, baseball is like is a national sport in the United States. These teams are flying from Boston to Oakland, back to New York, and so on and so forth. Okay, so essentially what you do here is you minimize the home, you have to find these feasible solutions which are tough, and at the same time, you have to optimize a complex objective function which is global. And the tension between these two things is what makes this problem very hard. Okay, so the input is very simple. You have n teams, okay, and you have a matrix which basically expresses the distance between the travel distance between every two teams. Okay, so I can index that matrix, okay, which I will call D in this lecture, which basically tells me the distance for traveling point from team A to team B. Okay. Now, what I want as the result is a double round robin schedule, okay, and that means that every team has to meet every other team twice, once at home and once away. Okay, so basically double round robin. Okay, and the other way to think about it is that the season is basically divided in a number of weeks, and every week every team has to play against another team. Okay. So we have essentially two types of constraints. The first one being the most difficult, okay, which is essentially the home and away pattern. Okay, so you don't want to play too many games at home or away. Okay, if the team is away all the time, the fans lose interest. If the team is playing too many games at home, the fans are losing interest as well because they don't want to go to the stadium 3 days in a row, right? So after 2 days, you get enough of eating popcorns and hot dogs and things like this. Okay, so essentially, you want to have a limit on the number of successive games that you can play at home, the number of successive games that you play away. Okay, so that's the first constraint. The second constraint is the no repeat constraints. If A plays against B, on a particular week, you don't want A playing against B, even at B stadiums on the next week. You don't want these two teams to play each other just two successive weeks. You want to spread that out such that you make the schedule more interesting. So these are the two feasibility constraints that we will deal with, and then the objective function is going to minimize the travel distance, okay? So every week a team is going to play against another team, okay? And it has to, sometimes it doesn't travel, sometimes the team has to travel, and therefore you want to minimize this travel. And I'm going to illustrate that on a particular schedule. So this is essentially everything you need to know to understand this problem. This is essentially the schedule for a TTP with 6 teams, and obviously if we have 6 teams, since they have to play against each other twice, we will have 10 weeks. So you see the 10 weeks, On the top, you see the 6 team over there. Every one of these rows is going to be the schedule of one team. And I want to go with you over, the schedule of one of these teams. So you see team 1 here. Team 1 is going to first play at home against team 6. And then he's going to move away and play at the stadium of team 2. So the 2 over there is basically telling you that team 1 is playing at the stadium of 2. Then team 1 is going to fly back home, okay, and plays against team 4. He's going to stay at home and play against team 3. And then he's going to take this completely crazy road trip, okay. So first moving and playing at 5, then moving from, the stadium of 5 to the stadium of 4, playing at 4, then flying and playing against 3. That's, again, away. So you have a sequence here of 3 away games. Then, team 1 is going to fly back at home and play 5, and then 2, and then conclude the season by playing at 6. Okay? So essentially what you see there is that the team is playing sometimes home, then fly to play, in some other stadium, fly back home, play a sequence of game at home, flying back away, can play a sequence of game away, which basically means that in those cases you fly from one away stadium to another away stadium and so on. Okay? Now, that's essentially the schedule of one team. Obviously, you can look at this thing from the week standpoint. So the first week here, you see all the games. So we already know that 1 is playing against 6, right? So obviously, we also want to make sure that 6 is playing it against 1. That's a game, right? So if 1 plays against 6 at home, we have to make sure that 6 plays away at 1, right? And that's what you see in this particular column. We also see that team 2 here is playing 5, okay, which basically means that team 5 is going to play at 2, away at 2. And of course, there is only one game which is left, which is 3 is playing at 4, and obviously 4 is playing at home against 3. Okay, so this is a double round robin problem. Okay, so every team is going to play every other team twice. You see the schedule of one team here. You see all the games that you are playing every week of the season. Okay, now you have seen also the various constraints that I've shown you, right? So in this particular case here, we see a sequence of 3 away games. We can't have 4. So this particular schedule for team 1 is basically satisfying all the feasibility constraints. Okay, we never go away and play 3 games, away, more than 3 games away, and we never stay home and play more than 3 games at home. We also never play against a team just next to each other. We play 6 at the beginning of the season and then at the end of the season. Okay, so that's basically what the TTP is about from a feasibility standpoint. Okay, so this is one of the aspects. We saw the feasibility aspect. What we have to take into account as well is the objective function. What you see here is essentially the total distance which is traveled by team 1. Okay, so when you look at the schedule, team 1, so playing at home against 6 at the beginning, then moving at 2. So you see that the first travel that this team has to do is moving from 1 to 2. Okay, then obviously the team is playing at home against 4. So the team has to fly back home. And what you see there is the distance from 2 to 1. We have to sum that. Okay, so the team is playing then at home against 4, at home against 3. So nothing happens there, no travel. Then the team has to play at 5. So which basically means that the third term that you see there is the travel between 1, the stadium of team 1, to 5. And that's the distance that you have there. Okay, and that corresponds to the schedule where the team is traveling to 5. Now from 5, the team is playing away after that at 4. So you have a travel which is between 5 and 4. And that's the next thing that you see in this particular sum. Okay? So that's how you compute this objective function. Okay? And this is only for the first team. But what you have to do is essentially compute that for every team. So you get this gigantic objective function, summing all this travel distance for all the team every time they move from home to away, or from an away stadium to another away stadium, or away to home. Okay? And so we have to sum all this, and this is essentially the objective function that we are trying to optimize. So to summarize, we have these feasibility constraints on the schedule, then we have this basic objective function that we have to satisfy, and we have to solve these problems. So now you can get a feel why this is so complex, right? So you have these crazy, feasibility constraints, and we have this gigantic objective function. Okay? Now you can solve this, you can try to solve this with constraint programming. It's a good exercise, so try it. But what we're going to do now is trying to see how we can solve this with local search. And one of the things that I want you to think about is what kind of neighborhood should we use, okay? So it's kind of crazy, right? So you can't just pick up a particular slot there and change the value. Or it's kind of funny, you know, swapping these two things here doesn't mean very much because there are a lot of complications here, right? So when we are trying to design this neighborhood, we need a little bit to think about what this whole thing means, right? And so what I'm going to show you is actually a complex neighborhood which has multiple moves, okay? Not a single move, but many moves. And that's what makes this problem really interesting. So I'm going to show you, you know, essentially 5 types of move. So you can swap ohms, swap rounds, swap teams, and then swap partial rounds and swap partial teams. And I'm going to go over every one of them to show you the beautiful neighborhood that we are defining for this problem. Okay? The first one is the easiest one, right? So what we want to do is that we see here that team 2 is playing at 4, and obviously team 4 is playing against 2. And that's you know, inside week 5 of the schedule. And in week 8 of the schedule, these teams meet again. We know that they have to meet twice, once at home, once away, okay, for one of the team, for both of the team actually. And so that during week 8, what we know is that team 2 is playing against 4 away, and obviously team 4 is playing 2 at home. Okay? And so this particular swap means that this particular neighborhood means that we want to change essentially the home away pattern. Okay? So instead, at the beginning of the season of having team 2 playing at 4, we want to have team 2 playing at home against team 4, right? And so we are basically changing these things, and we get this beautiful schedule now where, you know, team 2 plays at home first and then away against team 4. Okay? So that's the basic idea. Yeah. So that's a very simple move because it's essentially very local, right? So you only basically affect these particular 4 slots. Okay? So we're going to do a much more radical move, which is swap rounds here. Okay? So you look at a particular week and you look at another week. Okay? So in this particular case, it doesn't really matter when. So you could take these two things and swap them entirely. Okay? So you may violate some of the constraints, or you may change now the objective function, but you can swap them and still have a round-robin schedule. Okay? So you still preserve the round-robin schedule, and that's good. Okay? So in a sense, you know, when you think about this neighborhood, the moves are always going to keep, you know, the round-robin schedule satisfied at all the time. Okay? So what we may violate are the home-away pattern, and obviously we will change the evaluation function because every time we swap 2 rounds like this, the traveling patterns may change as well. Okay? So this is a very simple move as well. We take one particular round, we take another round, we just swap them. Okay? Now the next move is actually pretty interesting. We look at team 2, we look at team 5, and we say, well, you know, why don't we just swap the schedule of this team? It's a radical move, right? So instead of having 2, you know, played schedule, we're going to change this schedule and use the schedule of 6. Okay, or 5 in this particular case. And for the same thing, for 5, we use the schedule of 2. Okay, so we basically look at the schedule of one team, the schedule of the other team, and we swap them. Okay? No, there is a little bit, you know, you can't swap the whole thing completely, obviously, because 2 and 5 are going to play each other, so you keep these games. Okay? So in this particular case, it's very convenient because the game between the 2 of them is the first day of the first week of the season and the first week of the season and the last week of the season. So you can essentially, so you have these big blocks that you can just swap. Okay? But the day, you know, the game between these 2 teams could be the middle, so you would swap everything else. Okay? Now, when we do that, okay, so if we apply this thing, okay, so we get this beautiful schedule at the bottom. But now there is something actually very interesting happening, right? So you see 2 here, which is playing at 3, right? And obviously what we would like to, and before, okay, so 2 was playing at 1. Okay? So when you look at this new schedule, we also see that 1, you know, is still playing at 2. So we have 2 playing at 3, but we have 1 playing at 2, and that's not a game, right? So what is happening here is that we switched the games of these 2 teams, but they were the opponent of these 2 teams, and those have to be fixed as well. So you have a bunch of other entries in this table that needs to be fixed. We have to make sure that when we swap these schedules, we are also swapping the opponents of these 2 teams, the teams that they were playing against. Okay? So in a sense, that's what you do here. You fix all these guys, you swap them, and you get this beautiful table where essentially you swap these 2 these two teams, the schedule of these two teams, and you fix, and these are the blue entries there, okay? You fix all the other opponent. So it's kind of a complex move in the sense because you not only swap the schedule of these two teams, but you have also to adjust the value of the opponent, okay? So what you can see here is that it affects a huge part of the actual schedule, right? So it's a big move, okay? So one of the things that we're going to do now is look at these moves, especially the swap rounds and the swap teams, okay, and try to make them a little bit more fine-grained, okay, such that we can do smaller moves instead of affecting the really large part of the schedule. And this is what you are seeing here, okay. So we want to swap a round, but not the entire round. We want to swap a subset of that round. Okay, for instance, some of the constraints may be violated for these things, okay, or the distance is very bad for these two things, and we just want to swap these two, right? So we don't want to swap the rest of the round, okay? So here we say, okay, so I want to swap, the fact that team 2 is playing at 1 in week 2, okay, and the fact that it's playing at 6 in week 9. So I want really to swap these two things, because that would give me, let's say, a distance which is much better, okay? So I want to do that, okay? And so if I do that, what's happening? If I actually swap these two things, okay, so I would have essentially, the value here, which is 1, I would have it on this particular week, on week 9. But of course, on week 9, I already have a game with 1, right? So we have to fix that as well, okay? So we have to make sure that I'm not only swapping these two guys, but I'm constrained also to swap these two guys. Otherwise, I would be having 2 1s on this particular week, and that's not good, okay? So 1 would be playing at home and away in this particular case, so I have to swap that. And obviously, I'm changing the opponent of these guys, so I have to actually fix those guys as well and swap those guys as well. So the way to view this is that, in a sense, if I want to swap 1 and 6, I have to look at the connected component between these things. I'm looking at how they are connecting with each other in terms of the teams that they are already playing. And what you see here is essentially this round can be decomposed in several components. One of them is involving team 1, 2, 6, and 4, and the other one is involving team 5 and 3. So what I'm basically swapping are all the games involving 6, 1, 2, and 4, and I'm basically keeping the games between 5 and 3 in this particular case constant. And that's what you see here, okay? So you see that Team 3 and Team 5 are not affected by this move because they are not connected to 6 and 1, which were the two variables that I wanted to keep. Okay? So this is this move. So it's a more interesting move, right? So it only, basically swap partial part of these two rounds. And so it's more flexible. You can actually select a little bit more carefully, how you affect the schedule. Okay? Now the last move is actually the most beautiful one. This is swap partial team. Okay? And once again, what you see here is that I want to swap some part of the schedule between 1 and 6. Okay? So I want to say, between team 2 and 4, sorry. And team 2 on week 9 is playing against 1, and team 4 is playing against 6. And what I want is that I really want team 1 to play against 6 at that part, and team 1 and team 4 to play against 1. So I want to swap these two guys. But if I do that, what's going to happen? So you know that you see 6 over there, and you see 1 over there. So if I put the 6 on top here, you can already see that 6 is already on week 4. I have already a 6 on week 4. So which basically means that I would be playing at 6 twice. Okay? So in a sense, if I do that, I know that I will have to change this guy, and also the same thing for team 4. I would have playing it once, twice. So I need to also take care of these moves and swap them between the two teams. Okay, so that's what I'm going to do. I'm going to say, okay, I have to swap these guys as well. But now you see that I'm introducing, 5 over there. I'm touching to team 5 over there. I'm also touching teams 3 over there. Okay, so that means that once again, I have two teams that are affected by this thing, so I will have to deal with those guys as well, and that's what you see that I'm doing here. So I have more swaps to do, okay? And so I keep doing this, and now at this point, this is isolated. I have done all the swap and restored the fact that every team is playing against, every other team twice, once at home and once away. So in a sense, by propagating the information, I'm basically making sure that I'm restoring a round-robin schedule, okay? Now, we have the same difficulty that I've shown you when we did the complete, swap teams, which basically means that I still have to fix the opponents of these teams, okay? So all these cells here are not correct, but I'm going to fix them in the same way we fixed them before, and now I get this beautiful thing here, which is the final schedule. So what is interesting here is that when you look at this move is much less drastic. That's, just swapping the entire schedule of the two teams. I'm only swapping some part of the schedule and some part, of course, of the schedule of the opponents of these teams on these particular weeks. Okay? And so that gives me a finer grain to actually modify the schedule. And this is really important when you try to solve these problems in practice and find very high quality solution. Okay? So now I just want to tell you that this neighborhood is actually amazing. Okay? So these are results of the TTP over time. I told you this is a very interesting and very difficult problem. So people have been competing in trying to beat each other on this problem. And what you see, actually you probably can't see, but that's not a problem. So you see essentially people, starting trying to beat each other on this particular problem, starting from 2001. And on these three problems, which are the larger initial instance, 12 team, 14 team, and 16 team, you see that the last solution that was produced by an algorithm using the neighborhood that I've shown you, and has not been beaten for, let's say, 5 or 6 years at this point. Okay, so it's really a very nice neighborhood. Of course, you have to use other techniques that I will talk about, in 2 or 3 lectures, but essentially this neighborhood is really powerful and really a nice way of actually finding very high quality solutions for these problems. The solutions which have been produced by this neighborhood have never been beaten so far. Okay, so at this point, what we have seen is a lot of different ways of actually defining neighborhoods. Very simple one, tiny one, where you just modify the value of a variable, swaps, and then we see some really complicated moves like the one we saw today, where we affect large part of the schedules, but not completely large part, but also something which are intermediary. And this is the key for solving some particular problems. So what we're going to see in the next couple of lectures is how we can actually escape local minimum. Okay, local minima, because so far the only thing that we have done is essentially applying these moves greedily. But if you want to find a really high quality solution, you will have to be a little bit more careful. Okay, see you next time.